Why is it more exhausting to lift a wagon up than to lower the wagon down? The answer to that question lies in the fact that you transfer energy to the wagon as you lift it, and you receive energy from the wagon as you lower it. Energy is an intangible physical quantity that can move from object to object, and people generally find it more exhausting to give energy away than to receive it. Energy is what's known as a conserved physical quantity, meaning that you can't create it or destroy it. You can only move it from object to object. Conserved quantities are very rare in nature, and energy is one of them. It's analogous to money. In a society with law-abiding citizens, money is pretty much a conserved quantity as well. You can't create it or destroy it, usually without going to jail. And it's the conservation of that quantity that makes it so interesting. If people could print money at will, why, money wouldn't be very interesting anymore. Similarly, if you could create or destroy energy at will, no one would care about it anymore. Well, society decided to make money a conserved quantity. Society had no choice in making energy a conserved quantity. That's the way our universe works. And any civilization that's sophisticated enough to have discovered the laws of physics will have found the concept of energy and will have exactly the same quantity in their minds. Just as you can learn a lot about how a community or an economy works by watching how money moves through it, you can learn a lot about how something works by watching how energy moves through it. We'll do just that with ramps in a few minutes. But first, I need to talk a little bit about what energy is and how it moves between objects. Since we're going to encounter several other conserved physical quantities in later episodes, I want to distinguish energy from those other conserved quantities. Energy is the conserved quantity of doing. The more energy you have, the more you can do. The doing that I have in mind is what physicists call work. Work is a common word that has many meanings, only one of which is what physicists refer to as work. That physicist's work is the mechanical means of transferring energy. Doing work is analogous to spending money. When you spend money, you're transferring money from you to someone else. The total amount of money present in the world doesn't change. It just moves from one place to another. Overall, it's conserved. When you do work on something, you transfer energy from yourself to something else. The total amount of energy in the world doesn't change. It just moves from one thing to another. Energy, which I've described as the conserved quantity of doing, is defined as the capacity to do work. And work is defined as the mechanical means for transferring energy. That circular pair of definitions isn't very satisfying at the moment, but as we begin to play with work and energy, it'll all begin to make clearer and clearer sense. So bear with me, even though I've defined energy as a capacity to do work and work as the means of transferring energy, it's all going to work out in the end. But first, I've got to take a look at what work is. So let me show you work. Work according to a physicist. To do work on the wagon, there are two requirements. I have to push on the wagon, and the wagon has to move a distance in the direction of my push. For example, if I put my hand under the wagon, push up on it, and cause it to move upward, I'm doing work on the wagon. I'm following the rules. I'm exerting an upward force on the wagon. You know this from experience, and you saw that the wagon moved a distance in the direction of my force. Therefore, I did work on the wagon, and that means I transferred my energy to the wagon. The total amount of energy around in the world didn't change, but it did move in part from me to the wagon. Now, this is analogous to what you do when you spend money, right? So this is my money, and I'm going to give it to the wagon. Don't spend it in one place. So the total amount of money in the world didn't change, but it moved from me, in part, from me to the wagon. Same thing when I do work on it. Energy moves from me to the wagon. Now, if I don't follow the full rules, I don't do work. For example, if I don't push on the wagon, I do no work on it. On the other hand, if I push on the wagon, but it doesn't move a distance in the direction of my push, I do no work again. So I am pushing, or don't watch for a second. Let me get this up here. Okay, now watch. Now I'm still pushing up on the wagon, but it's not moving. So I'm doing no work on it. And actually, I don't have to make sure that it's not moving altogether. I just have to make sure that it's not moving in the direction of my force. So since my force is upward, if it moves horizontally, that's not in the direction of my force. I do no work. So let me get it started. But now as it coasts to your right, I'm doing no work on it. Now let me get it going to the left. Again, it's coasting to the right. My force is straight up, but it's moving horizontally. Those are at right angles to each other. I'm doing no work on it. Now you wonder, why is it tiring to sit here holding up a wagon? That's because human beings are not statues, and we burn calories just trying to hold a pose. So I'm not transferring energy to the wagon, but I'm getting tired nonetheless because I'm turning my own chemical energy into thermal energy. I'm getting hot holding this here all day. That doesn't affect the wagon. The wagon's just minding its own business with the same amount of energy now, because I'm doing no work on it. Now that you've seen how work works in the context of wagons, let's apply it to another situation, rubber bands. So here's a question for you. If I hold one end of the rubber band motionless with my left hand, and I take my right hand and stretch the rubber band outward like this, which of my hands is transferring energy to the rubber band? Your right hand, the one that holds a piece of rubber band that moves, does work on the rubber band. The other hand, the one that stays still, doesn't move and therefore does no work. So, as I move the rubber band to your left with my right hand, sorry for the complexity here, this hand is doing work. It's pushing the rubber band to your left. As the rubber band moves to your left, those are the same direction. My hand here is doing work on the rubber band. The other hand doesn't move, does no work. We've seen that when you push on an object and it moves in the direction of your push, that you do work on it. And that means you transfer your energy to it. But what if it moves in the direction opposite your force? Like this. I'm pushing up on the wagon, but it's moving downward. What then? In that case, you do negative work on the object. That is, you transfer less than zero energy to it, and you reduce its overall amount of energy. Is there a money analogy to this? Sure. We've seen that the money analogy to doing work is to give money. So doing work on the wagon and increasing its energy is analogous to giving money to the wagon and increasing its money. Okay? Doing negative work on the wagon is equivalent or analogous to giving the wagon debt, to giving it less than no amounts of money. For example, my car loan, it's weighing me down. If I give it to the wagon, I weigh it down. My money just increased. I'm happy. The wagon, suddenly saddled with debt it didn't expect, is impoverished. I can give it my mortgage. I can give it another mortgage on the summer house. And, hey, maybe a loan for college. So, I have passed along negative money to the wagon. It's poor and I'm richer. This is great. That's analogous to negative work. Whenever you do negative work on something, you lower its energy, and amazingly enough, you increase your own. Well, how did I increase my energy by doing negative work on the wagon? I'll show you. I'm about to do it. The wagon right now has some energy, and as I lower it, and therefore do negative work on it, watch what it does to me. It's pushing down on my hand, and my hand is moving downward. It's doing work on me. So, at the same time I do negative work on the wagon does an equal amount of positive, that is, work on me. And that's how the energy moves. Whenever one object does positive work on the other, the second object does negative work on the first. There's a perfect transfer of energy from one to the other. And overall, the total amount of energy doesn't change, it just moves. That brings me to one last point. I've talked about doing work and doing negative work. Shouldn't the word positive show up in here? Shouldn't this be positive work and negative work? Maybe. But physicists have adopted the convention that if you don't specify negative or positive, we assume positive. And that just simplifies the language. So doing work always refers to doing a positive amount. If you're going to do a negative amount of work, say it. Use the word negative. And you might think, well, that's a silly convention. No one ever adopts that convention outside of physicists. Well, think about charity. When you give money to charity, we're assuming you're giving a positive amount of money. Don't you go giving your loans and your mortgages to a charitable organization. They're not going to be happy about that. I've been talking a lot about work and letting energy come along for the ride, but it's time to reverse that arrangement. Let's talk about energy. And to do that, let's revisit the rubber band problem. When I stretch a rubber band, the rubber band changes. When it's unstretched, okay, can't do anything. But once I stretch it, it has something it didn't have before. Not more mass, not more weight, not more speed, more ability to do things. And energy, after all, is the conserved quantity of doing. This rubber band, now that I've stretched it, is capable of doing work and making things happen. Energy takes two principal forms, kinetic energy and potential energy. Kinetic energy is the energy associated with the motion in objects. Now, energy itself is the conserved quantity of doing, not of moving. So energy isn't inherently about motion. But there is energy in moving objects. For example, this ball. When the ball's at rest, it has no energy associated with motion because it's not moving. But if I do work on it, I'll push it to your right and it will move toward your right. And during that brief period while it was passing quickly to the right, it was chock full of kinetic energy. That is, it had energy that was in the form of this energy of motion, kinetic energy. So the whole act of throwing the ball from one hand to the other involves investment of energy in the ball. So I'm transferring energy to the ball by way of work. It then moves. It's carrying its energy with it as kinetic energy. And when I catch it, I take the energy back out by doing negative work on it. So long story, simple action, but there's energy going in and coming out. So moving objects have energy associated with their motion. That is called kinetic energy. But even objects that are at rest can have another form of energy. Potential energy is energy stored in the forces between or among within objects. So forces can store energy. For example, there is a gravitational force or attraction between this ball and the earth. You know that because we've talked about you drop the ball and it falls. So the ball is being attracted to the earth is being attracted to the ball, and if I pull them apart, something that takes work to do, I invest energy in the ball in the form of gravitational potential energy. That is, an energy stored in the forces of gravity, in this case between the ball and the earth. So when the ball is down low, it has relatively little of this gravitational potential energy, and as I lift it upward and do work on it in the process, I'm pushing it upward as it moves upward, I'm increasing its total energy, and that energy is going primarily into the form of gravitational potential energy. The energy stored in the forces of gravity. I tend to identify the forces involved in a potential energy. In some cases, people simply refer to potential energy generically. But if we can, it makes sense to identify the forces that are doing the storing. So that's gravitational potential energy. Let me show you elastic potential energy. Energy stored in the forces of an elastic object. I hope you had one of these cans of mixed nuts when you were young. And you would go up to your favorite aunt or uncle and say, Uncle Richard, would you like some nuts? I have them. Hear them rattling? And then you would open the can and out would jump a snake, right? And then you would laugh. Everyone would laugh. You would stick it back in the can. And 5 minutes later, Uncle Richard, want some nuts again? And he would be surprised yet again. Well, okay, so fun and games. But that energy that caused this snake to leap out of the container and attack my magnets down there on the table, that's energy stored in the elastic forces within this snake. And I'm doing work, pushing the snake back in as it moves inward. I'm packing it full of elastic potential energy, and it's ready to attack another relative. Okay, elastic potential energy. Another familiar situation with elastic potential energy is an elastic balloon. If I inflate this balloon with air, an action which requires work, I pushed the skid outward by way of my air, and it moved outward. So I did work on it. It's now has energy stored in the elastic forces in the balloon surface. And if I let go, off it goes. It uses the energy that I put in to do something, fly around the room. Other forces. The forces between magnets. We can store energy as magnetic potential energy. These magnets are attracted strongly to one another. They're as close as they can get. I have to pull them apart. Something that's not easy to do. I'll get them apart. There, they're apart. And that action took work. I pulled them apart and they moved apart. So I've invested energy. They now have it in the forces, the magnetic forces between them. So magnetic potential energy. And if I let them come near each other, off they go. They release that energy, leaping at each other. The energy transformed spontaneously from magnetic potential energy to kinetic energy, because suddenly we had some fast-moving magnets, and then into sound and other forms of energy. How about the forces between electric charges? So that's the forces between magnets, magnetic poles, something for the future. How about the forces between electric charges? Well, this is a device that stores separated positive charge and negative charge. And I'm going to, right now, the charges are evenly distributed here. There's nothing special going on. But I'm going to separate positive and negative charges from one another. And if you remember the old opposites attract, well, opposite charges attract. And I'm going to separate them with the help of this collection of batteries. Batteries can do work on electric charges, and that's what I'm going to let them do. So here they go. The batteries are now doing work, pulling apart positive and negative charges, accumulating negative charges on this side, accumulating positive charges on that side. It's an arduous process because this stores a lot of separated charge. Here we go. It's pretty well separated at this point, and I'm going to stop that process, and I'm going to let them get back together. The energy is stored as electrostatic potential energy. So frequently this would be called magnetostatic potential energy. That's full of electrostatic potential energy. I'm going to let that get together. Ready, get set, got together, and energy was released. Last form of energy to talk about here, because I'm going to leave nuclear potential energy for some other situation. I can show it to you, but then I'd have to do something. So, ready? Chemical potential energy. Must be a dud. Okay, so you get the idea. Energy can take two principal forms, that is kinetic energy, the energy of a moving object, and it can take potential energy, that is energy stored in the forces between, within, among objects. There are a variety of forces to work with. We've worked with several of them, and those forces can store energy. Often when the energy is being stored in potential form, there's no motion at all. When there's kinetic energy, of course, there is motion. And the last observation to say about energy is, energy as a whole is a conserved quantity. You cannot create total energy, you cannot destroy total energy. But the individual types of energy, they're not conserved. So kinetic energy can change as long as potential energy changes correspondingly in the opposite direction. Similarly, you can turn chemical potential energy into kinetic energy. You can turn kinetic energy into gravitational potential energy, like that, and so on. Don't try to conserve the individual pieces of energy, the types. It's total energy that is truly the conserved quantity in nature. Like any object, a wagon has kinetic energy when it's moving, and it has gravitational potential energy when it's elevated. Now, in the context of ramps, we're doing a lot of lifting of wagons, and so knowing how much gravitational potential energy the wagon has at various heights is going to be useful to us in understanding what ramps do, how they make life easier. So, let's figure out how much gravitational potential energy the wagon has at various heights. To do that, I have to start by making sure it's clear exactly how much work you're doing when you lift that wagon. Work, I've told you, is force and distance. That is, to do work on this wagon, I have to exert a force on it, and it has to move a distance in the direction of my force. The exact amount of work I do is the product of the force I exert on the wagon times the distance it moves in the direction of that force. Now in this case, it's moving exactly in the direction of my force. My force is straight up and it's moving straight up. Life is simple. But if I push the wagon upward and it moves up at an angle, the overall distance the wagon moves isn't the issue. What matters is the component of its motion that is in the direction of my force. Since my force is straight up, the only part of the wagon's motion that counts is its motion in the upward direction. Its motion horizontally doesn't matter. It doesn't contribute to the work. So, the amount of work I do in lifting this wagon is the force I exert on it times the distance it travels upward. Its increase in elevation or altitude. That's interesting because in order to lift this wagon upward at constant velocity, I have to push upward with a force that exactly cancels the wagon's weight. So as it goes up steadily, I am pushing up with a force equal in amount to the wagon's weight, although in the upward direction, and it's moving upward directly in line with my force. So the work I'm doing is the product of the wagon's weight times the upward distance it moves. That's very simple. I'm doing that work, and that work is becoming entirely gravitational potential energy in the wagon. So starting with a clear understanding of work, that it is the force you exert on the wagon times the distance the wagon moves in the direction of your force, we can then figure out how much gravitational potential energy the wagon has at any given height. It's simply the wagon's weight times its increase in altitude. So, it turns out we have to set a zero of gravitational potential energy, because this, we might call this 0, but actually if I drop the wagon on the floor, I can release a little bit of gravitational potential energy that's even there at 0. So we choose a 0, and if you really want to, you can go into the negative values by coming off the table. But this is a perfectly good 0 right here. We don't have to worry about going to the floor or going to the basement and so on. Start at 0 here. If I increase the height of the wagon by 1 meter, then, and I suppose I had to push up on this wagon with the force of, let's say 10 newtons. So a 10 newton force upward times 1 meter of upward motion, that is 10 newton meters of work that I did on it. Now, the newton meter has a name. It is the unit of energy. It's got a name to make life simple. It's called the joule. So in lifting this wagon 1 meter upward using a 10 newton force, I did 10 joules of work on the wagon, and they are now present in the wagon as gravitational potential energy. The gravitational potential energy of the wagon increased by 10 joules in going from here to here. It's time for the question I asked you to think about in the introduction to this episode. When does the wagon have the most energy? When it's at the bottom of a long ramp, the top of a long ramp, the bottom of a tall ramp, so the ramp ends here, or the top of a tall ramp? By being at the top of a tall ramp, the wagon has as much gravitational potential energy as it can have among the choices I offered. So, by getting here to the top of the tall ramp, it's accumulated as much energy as it can accumulate. The work you do in lifting a wagon depends only on how much you increase its altitude, and not on the specifics of how you did that lifting process. Whether you go up the ramp or you go straight up doesn't matter. It's just the increase in altitude that matters. And the work you do is the weight of the wagon times the increase in altitude. That means that as you go up the ramp, you must be doing work on the wagon because you're increasing the wagon's altitude and therefore its gravitational potential energy. As you lower the wagon down the ramp, you must be doing negative work on it because you're decreasing its altitude and therefore decreasing its gravitational potential energy. We're now in a position to answer the question I asked at the beginning of this video segment. As you take the wagon up the ramp, you're doing work on it, increasing its gravitational potential energy, and doing work on a heavy load involves transferring a lot of your energy to the wagon. And so you're using chemical potential energy in your body, energy that you receive from your food. You're consuming that, you're transferring it mechanically into the wagon, and that transfer is tiring. It wears us out, it fatigues our muscles, it consumes our energy. As you lower the wagon down the ramp, an action that requires negative work, you're taking energy out of the wagon and receiving it yourself. It's coming into you. Now, human beings, like most animals, cannot store energy well. So the work is really being done on us. We are receiving energy as we lower the wagon down the ramp. And what we do with that energy is to waste it. We turn it into the waste version of energy, the most degraded, useless form of energy, which is known as thermal energy. Thermal energy, as we'll deal with in the near future in other episodes, is ordinary energy chopped up into little pieces and scrambled and sprinkled among all the particles that make up your body in this case. And thermal energy is hard to do anything useful with. It's energy, but it's disordered energy. And you can't get it ordered together to do work. Or not easily. So, taking the wagon up the ramp involves you transferring energy to the wagon. That's tiring. Taking the wagon down the ramp involves the wagon transferring energy to you. That has some tiring aspects to it, but at least it's not consuming the same amount of your stored chemical food energy, and it's less exhausting. It's a little nerve-wracking because you can get injured as that energy rushes into you, but it's not as fatiguing.